Okay, let's continue with the third chapter. Today we're going to discuss something called cellular automata. Okay, this is also the title of section 3.3. And cellular automata is also called CA. I mentioned this concept a little bit before when we were talking about Conway's game of life, right? So here, let me introduce it officially. So CA, they are discrete spatial temporal dynamic systems based on local rules. So here is an example of CA. I believe you have seen this in NetLogo, right? We have a lot of cells. Each cell is considered as an agent. So this model here is called agent-based model, ABM. But actually, the official name for each cell here is cellular automata. Okay, so each one is a cellular automata. So this whole space is full of cellular automata, and each of them is following a set of local rules to change its state. Okay, CA can generate very complex spatial temporal dynamics from relatively simple rule sets. How complex is that? Later, I will give you examples. But you should know that that's why CA is powerful. If you provide a pretty simple set of rules, all those small cells, they can provide very complex processes and patterns, okay? And the game of life is one example, and we're going to talk about game of life in detail later in this section. And the CA was proposed by Van Neumann, John Van Neumann. He was a genius, okay, literally a genius. And he was a mathematician, physicist, computer scientist, and polymath who created CA without the help from computers. Okay, so back then the computer was not something common, and he proposed this idea and used his pen and paper to create something very complex like this, and we're still using, and it's still using it today, and it's the foundation of artificial intelligence. And some basics here. CA basics. So cell, a basic unit that be in one of a finite set of discrete states, right? Could be 0, could be 1, or could be any discrete state. And there is also a lattice of cells. The cells are arranged in a regular discrete spatial configuration, usually a lattice. Not necessarily, but in this course, this lattice is full of cells, okay? And each cell is a discrete spatial object or agent, okay? And neighborhoods, they are important because I mentioned at least Van Neumann neighborhood and Moore neighborhood previously. And of course, there are other methods to define neighborhood. And for example, extended Moore, a Moore neighborhood with radius equals 2, which means a larger Moore neighborhood, or arbitrary, right? As long as you have your reasons, you can defend your reasons. You can define your own neighborhood for your own research, for your own application, right? Examples here, right? On the top left, we have a very typical 3x3 Moore neighborhood. Usually the central pixel is the one you're interested in. And based on this cell, based on this pixel, we have this Moore neighborhood with 8 cells surrounding it. And this is a very basic 5-cell Van Neumann neighborhood, okay? Only cells on cardinal directions or orthogonal directions, they are considered neighbors of the central cell or central pixel, or call it automata, right? It has a lot of names. And here to the right, we have an extended Moore neighborhood. Instead of 3x3, now it's 5x5. Obviously, this is making the neighborhood more complex than 3 by 3, more neighborhood, but you can also use it if necessary. What does it mean if you compare 3 by 3 more neighborhood and 5 by 5 more neighborhood? It means that for 5 by 5 more neighborhood, the central pixel or the automata receives influence from even pixels further or cells further away, right? Because all these pixels 2 units away from the central cell can affect its value. But in a 3 by 3 more neighborhood, only 8 pixels, 1 unit away from the central pixel can affect it. Okay, so a larger neighborhood means that the local influence can be brought by cells, by pixels further away from the central cell, okay? The conditions in the neighborhood of each cell at time t determine its state at time t plus 1, which means that the current state of automata of its neighborhood will affect the value, the state of the automata after next tick, t plus 1, right? And here is another example of say A with specific context, right? For example, yeah, right now it's just a time we're experiencing a very serious pandemic, COVID-19, right? Here is an application of say A in the spreading of disease, right? We have 3 states here for each cell. Susceptible state, which is blue, is addressed by blue. Incubation state, green. It means that people may have been infected, but there is no symptoms for now, but maybe in future, right? And red is for infected state. I'm not an expert, but maybe incubation is not what I said, but it's somewhere between susceptible and infected. But anyway, red is for infected state. So we have 3 states here, right, for each cell. And you can say if a cell is infected, right, and you define this more neighborhood, it could affect other people or other cells surrounding it. Okay, some of them they are already green. Okay, they are on their way to red, and some of them have not been infected. Maybe they're immune. Maybe it's just time is not right. Maybe in future they will be in incubation state. But anyway, this is a research from some scientists. They proposed the CA model to simulate SARS. Okay, SARS. That's another pandemic happened in 2004, 2003. Okay. So let's talk about transition rules. We usually talk about a specific central cell or a cell of interest, and we discuss how its neighborhood affects its own state, right? And there will be transition of states for each cell, right? And how to address those rules for transition. So determine the state of a cell at time t plus 1 based on the conditions in its neighborhood at time t. The transition rules are finite and constant across all cells, which means that all cells, they're equal to each other in terms of transition rules. Once you have created a set of transition rules, it will be applied to all cells on this lattice, okay? And we have 2 categories of say A's we want to talk about in this class. And we're going to say how to create transition rules for them, okay? Okay, so the first type is called simply say A or standard say A. Let's just call it say A. Transition rules, they are based on the spatial pattern of states in each cell's neighborhood. Okay, but there is another category of say A is called total say A. The full name is called totalistic say A. Transition rules, they are based on another thing. They're based on the total or sum of states in each cell's neighborhood. It's not based on spatial pattern of states. It's based on sum of states in each cell's neighborhood. So there is huge difference between these two, say A or total say A. Okay, and if we're talking about altered total say A, it means that the rules includes the value of the focal cell or the central cell. Okay, it means that when we're talking about the state of the central cell at t+1, usually it is only related to the states of its neighborhood. But if we are talking about altered total say a cell's state at t+1 is also decided by its own state at t. Okay, but let me give you examples of a very simple example of say A and total say A. Okay, let's get back to this. Okay, so this is a very simple example for say A. Okay, let's just say we use K to represent the number of states for each cell. Since K is equal to 2 here, it means that each cell could be 0 or 1. And H is the number of what? Of neighbors for each cell. So here I have created a very simple example for say A. For each cell, we have 0 or 1. Okay, the cell with the question mark is the central cell, is the cell we care. And since H is equal to 3, it has 3 neighbors. The 3 neighbors, they are right above this central cell. Neighbor 1, neighbor 2, neighbor 3. This is a very weird neighborhood I designed. You can consider this as a user-defined neighborhood. I don't want to make it complex because even we use von Neumann neighborhood, there should be 4 neighbors, right? It's just too complex. So I designed this user-defined neighborhood. So this is the central cell. This 3 cells above it, they are neighbors. And each cell has 2 states because K is equal to 2, right? So if a cell is occupied, it's 1, then it is painted black. If a cell is empty, right, then we consider the state of this cell as 0. So black 1, white 0. So how many patterns are there? Right? There should be p patterns. And p is equal to k to the power of h. So k is equal to 2, h is equal to 3. 2 to the power of 3 is 8. So we have 8 patterns, right? So the pattern 1 is 1, 1. Now we're talking about the neighborhood, okay? So the pattern 1 for neighborhood is 1, 1, 1. Pattern 2 is 1, 1, 0. Pattern 3 is 1, 0, 1. So if we exhaust all the possibilities for the spatial pattern of the neighborhood, we have 8 patterns. They're all here. Okay, so this is say A, just regular say A. Okay, so this is an example. Let's get back to the slides. Okay, why do we that was the example of say A, right? But there is another type of say A called total say A. Why do we need total say A? Because say A seems simple, but are very complex. The number of possible rules is enormous. Okay, for example, in say a number of possible cell patterns in a neighborhood can be addressed by this formula. I have shown you this formula in that spreadsheet from Excel, right? P is equal to K to the power of H. K is the number of possible states. In our example, it is 2. H is the number of cells in the neighborhood. In our example, H is equal to 3. So we have 8 patterns. Okay, let's continue. Let's continue. And since each pattern can result in the cell of interest being in one of K states, the number of possible rules is R equals K to the power of P. So K is 2 in our example, right? What is the value of P? P is 8, which means that we have 2 to the power of 8 rules that can be set for that very simple say I just showed you, which means there could be 256 rules. How is that? Let's get back. Okay, so for each pattern, you can give a value for the cell you care, for the central cell, the cell with the question mark here. So for pattern 1, let's just make a rule here. Rule 1. For each rule, you should assign a value for each pattern here, and you are the god here. You can assign any value to the cell you care. But since we only have 2 possible states, its value could be either 1 or 0, right? So let's just say for pattern 1, 0. For pattern 2, also 0. For rule 1, no matter the pattern, I will assign 0 to all patterns here, okay? This cell here, this question mark, is always equal to 0. That's rule 1, okay? How about rule 2? This time, for this pattern, still 0, 0, 0, 0, 0, 0, 0. But for pattern 8, which means that if all 3 neighbors, they are all 0, this time, the central cell will be 1. Okay, now I have rule 2. So if I repeat this process, rule 3, rule 4, and etc., etc., etc. Eventually, if I exhaust all the possibilities for rules, how many rules will there be? How many rules will there be? Let's just look at the value of the central cell from another perspective. It can be 0 or 1. And now we have 8 patterns, which means that we have 8 digits for this binary value. So eventually, how many possibilities for this 8 digits binary value? Of course, 2 to the power of 8, which means that eventually we can create 256 different rules for this say for this 8 patterns of neighborhood. Okay, eventually this is the last rule. Rule 256 is all 1. So rule 1 all 0 to rule 256 all 1. So you can say that this is a very simple neighborhood. It has only 3 cells, and each one has only 2 states, 2 possible states, and eventually we have 256 rules. Okay, let's get back. So R is equal to K to the power of P. What if in a more neighborhood with binary states, K is equal to 2 still, H is equal to 9, more neighborhood, why is it not equal to 8? Because we're using alter say A right now. For alter say A, the cell, the central cell itself is also considered. So that's the reason why here H is equal to 9. Yeah, obviously it's arbitrary. You can change it to 8, but for this example, let's accept K is equal to 2, 0, or 1, 2 states. H is equal to 9. More neighborhood, 8 neighbors, and the cell itself, 9. 9 cells, right? There are 2 to the power of 9, which is 512 possible cell patterns. Now it's not 8 patterns, it's 512 patterns. So how many rules can you create? 2 to the power of 512. This is a very huge number. The number of possible rules for this say is larger than the number of elementary particles in the universe. So now, do you still remember that argument? Say A can create very complex spatial pattern, or not spatial pattern, any pattern with very simple rules. 2 states, a very simple Moore neighborhood. That's the possible rules, the number of possible rules you can create for this very simple, looks seemingly simple, say A. Okay, so that's the powerful part of say. That's also the tricky part of say A, because even with this very simple configuration, even for today, a normal PC you are using every day cannot deal with this huge number of rules. It's just too complex. That's the reason why we need total say A. It's simpler than say A, and it's good enough. And in totalistic say A, or in total say A, number of possible cell patterns in a neighborhood is also P, but this time it's smaller. Is smaller. P is equal to K minus 1, then multiply H plus 1. K is still the number of possible states. H is still the number of cells in the neighborhood. Okay, let me show you an example here using the same configuration. Okay, this is say A, right? We have talked about it. Let's go to total say A. So K still 2, H still 3, is still this neighborhood. P this time is K minus 1 multiplied H plus 1, which is 4, which means that according to total say A, there are only 4 meaningful patterns. Why? Because total say cares not about the spatial pattern of neighbors. It cares about the sum of patterns. What does it mean? So for this specific pattern, what's the sum of neighbors? Black represents 1, right? So 1, 1, 1. The sum of the neighbor is what? Is 3. But for the next 3 patterns, there are actually 1 pattern for total say A, because the sum of the neighborhood is the same. Because, for example, this is 1, 1, 0. What's the sum? 2. Although this is 1, 0, 1, the spatial pattern is different from this. But how about the sum? The sum is still 2. So if the sum stays the same, it is the same as this pattern for total say A, because total say A cares about the sum of neighbors. And similarly, if the neighborhood is 0, 1, 1, the sum is still 2. So these 3 patterns, they are 1 pattern for total say A. Similarly, pattern 3, what's the sum here? 1. Pattern 4, what's the sum here? 0. So here we have less patterns here. For say A, it should be 8 patterns, but we combine some of them because they have the same sum. Now we have only 4 patterns here. So now let's make rules for them. This time, it's easier. It's easier. So rule number 1. Okay, let's just say for pattern 1 is 0. For pattern 2, although there could be 3 different situations, they belong to 1 pattern. Let's just give it 0. Still 0. 0. Okay, let's get back to the slide a little bit. So now, still, and since each pattern can result in the cell being in one of k states, the number of possible rules, still this formula, R equals k to the power of p. R equals to the to k to the power of p. Okay, so root 2, 0, 0, 0, 1. So when we do this repeatedly, how many rules can we have? It's still binary, it's 0 or 1, but now we only have 4 digits, 4 patterns instead of 8 patterns, right? So now we have 2 to the power of 4, which means that we only have 16 possible rules. And the last one should be 1, 1, 1, 1. Okay, if you compare these two, the second one is simpler, much simpler. Rule 16. Here we need rule 256 and 56. Okay, so that's the difference between say A and total say A. Say A cares the spatial pattern of the neighborhood. Okay, total say A only care the sum of neighborhood, or you can say the sum of neighbors. Okay, so that's the difference. This is total say A. Okay, I think that's enough information for one video clip. Okay, I will see you in the next one. Thank you.